Okay, I think we can start. Okay, let us welcome Professor Thomas Sotiriou from University of Nottingham here. And as most of you know, that Thomas is a leading expert of black holes, modified gravity theories. He has worked extensively on these topics, and we are really happy and we are grateful that he has agreed to come here and give us this lecture. So enjoy with him. Thank you.
Thanks very much, Sudipta. Okay, so the idea is that out of the 5 lectures, the first 2 will mostly be black holes in general relativity. So simpler things that most of you will already have seen, and then we're going to move on to black holes beyond general relativity and how we could potentially deviate from the Kerr picture. So black holes are probably the most interesting objects in the universe, at least if you're working in gravity. So they have an interesting history, of course. It took a very long time for the idea of a black hole to be accepted. So already, as you probably know, already just a year after Einstein published his famous field equations, Schwarzschild derived the first black hole solution just by solving these equations explicitly in the static and spherically symmetric limit. But of course, at the time, nobody believed that this is a black hole. So the singularity on the Schwarzschild horizon took a very long time to kind of resolve. People use different coordinate systems to try to solve eventually that this is not a singularity. But I mean, I think all the way back, all the way probably to the 50s and 60s, I mean, for many people, understanding coordinate transformations, diffeomorphism invariants, and so on and so forth was still quite a challenging topic. There's a famous letter by Richard Feynman to his wife from a gravity conference in Warsaw, saying, you know, that I'm not learning anything in these meetings. In this meeting, there's a host of dopes here that don't understand anything, you know, and remind me to never go to a conference in general relativity again, on general relativity again, which kind of demonstrates kind of the fact that general relativity kind of become a bit of a niche field for, you know, from the perspective at least of theoretical or particle physics. Of course, I mean, Feynman was wrong in this case, because I'm sure you all know that the beautiful work done by Chandrasekhar, Oppenheimer, Snyder, Tolman, Volkov, and others in the 30s, 40s, 50s in understanding the structure of relativistic stars, understanding gravitational collapse, and hence showing effectively that collapse could, in fact, lead to black holes. Then later on, Penrose and Hawking and Penrose, of course, proved their famous singularity theorems that also kind of on the mathematical side of things showed that that singularities are inevitable, and hence, I mean, we shouldn't be too scared of the singularity in the center of the Schwarzschild solution. There was also wonderful work from Sarkar and then Sarkar and Jimmy York and others. I mean, trying to establish the well-posedness of the initial value problem in general relativity. So I take Einstein's equations, I try to write them as equations that can describe evolution in an appropriate notion in time, and show that there is a solution exists, it's unique, and it depends continuously on initial data. And of course, that was also very important to eventually try to numerically simulate collapse and show that black holes do form from realistic initial data, right? So all of this together convinced people that black holes actually exist, and by now, obviously, we believe we observe them in nature. So I gave this very brief introduction because I'm going to touch in one way or the other on all of these points in my lecture. So today I'm going to start with easy things, the Kruskal diagram. Okay. I didn't realize that this was. Okay. So hopefully you've all seen the Kruskal diagram that describes the extension of the Schwarzschild solution. Just going to write down the metric, the line element, so this is the Schwarzschild line element in usual Schwarzschild coordinates. So as we know, this suffers from a singularity at r equals to m, and we understand this now to be a coordinate singularity. So you've probably all seen ingoing Eddington-Finkelstein coordinates, where we introduce this v right? So we introduce v, which is a null coordinate. That means that when v is constant, we're looking at the paths of null ingoing rays, null hypersurfaces, which are ingoing light rays, right? And then there are also the outgoing Eddington-Finkelstein coordinates. So u so through this, so this is again another null coordinate. It corresponds to outgoing light rays. Again, we define these coordinates, of course, for r equals 2m for the regular part of the space-time. And then if you swap the time coordinate with either of these coordinates, then you can rewrite the space-time for the exterior in this way. Or that way. And each of these set of coordinates, the v are theta and phi, or the u are theta and phi, offer two different extensions of Schwarzschild, right? And both line elements that I've written down there are both regular at r equals to m. So, and that's how they offer the extensions. R equals 0 is singular in both cases. And you can calculate the Kreutzmann scalar. Riemann contracted fully with itself. And of course, it diverges at r equals 0. So both of these offer extensions, two different extensions of the Schwarzschild metric, and you can notice that if you take t minus t, that means that u goes to minus v, right? And hence, these two extensions are the time reversal of each other, right? If you make v minus u or u minus v, these line elements match, and one is the time extension of each other. So these are basically the Schwarzschild exterior plus a black hole region, or the time reversal of that, which is the Schwarzschild exterior plus a white hole region. Okay? How can I get two different extensions from the same space-time on the Schwarzschild exterior? Anyone wants to take this one? Why can I extend in two ways? Yeah, but I'm asking, how can I start from a single exterior and by introducing two different coordinate systems get two different extensions? which are the time reversal of each other. Why don't I get a unique extension? There must be some symmetry in the exterior, which is not a symmetry of the other two. Sorry? Yeah, exactly. So if you look at the original space-time, it is static and it's invariant on the time reversal. T2 minus T leaves in the line element invariant. This is not true for these two. So basically, I extended in the two ways that I could glue to the exterior, the forward or the backwards in time, which from the perspective of the exterior is, irrelevant. Okay? Okay, now of course the question arises, okay, I didn't follow the rule. Yeah, so this suggests to me that there must be some extension of Schwarzschild that includes both of these speeds and then some. And that comes by the Kruskal coordinate. So the obvious thing you could say here is, okay, I've introduced one coordinate to swap T. I've introduced the other coordinate to swap T, but what if I would use both U and V, which are the two null directions of spacetime, and have what we call a double null cover? So I could choose coordinates so yeah, immediately you notice that if you take the sum and the difference of U and V, then you can express them in terms of T and R separately. So you do know that you can swap then T and R completely for U and V. And you can write the space-time in terms of these coordinates, but it's not going to be very useful. Can anybody tell me why? If you look at the coordinate transformation. So I can take the original IM element, replace both T and R in terms of U and V, and just use this double null cover with U, V, R, and theta. But it's not going to be much of an extension. Why? What happens at R equals to M? You get a divergence here at R equals to M, right? Which means U minus V diverges, which means that if I'm trying to approach R equals to M either along a U equals constant surface or a V equals constant surface, which is in or outgoing null directions, then the other coordinate will just go to infinity or minus infinity, right? As I do this, so let me write it down. It goes to plus infinity along V equals constant. And V goes to minus infinity along U equals constant. So that's no good because it means that the horizon R equals to M corresponds to infinite coordinates along certain directions, which means this is a cover of only the exterior. I'm running out of coordinate when I'm trying to reach the horizon. So I could use this double null cover, V and U, but then I'm covering only the exterior spacetime. And this doesn't provide actually an extension. So I need to find a way to go further in, which I can do by a further coordinate redefinition. So defining capital U and V in this way. So through these exponentials, such that as R going to 2M, U is equal to 0 when capital V is constant, or V is equal to 0 when capital U is constant. So basically, by using these exponentials, I'm mapping the plus infinity of U and the minus infinity of V to zeros of U and V, and then I can extend my space-time by going to the negatives, negative U's and V's, and now I'm creating an extension which will hopefully capture the extensions that I had with the individual Eddington-Finkelstein coordinates. So the corresponding metric then takes this form. And UV is related to R in this way. Okay, so I've left, so if I just take that original line element and I make the successive coordinate transformations, I'll end up with this metric here. And the relation between R and U and V is given by that. You can also have the relation, obviously, between T and U and V if you use this equation and this transformation. So the reason I wrote this down is because I've left R implicit in the action, sorry, in the line element. So I obviously need this relation to just write the line element completely in terms of U and V, right? So one thing you might be concerned is, can I determine R uniquely with U and V? Okay, and the answer is yes. This is a known function called the Lambert function, and even though you can solve analytically for R, it is single valued for R larger than 2m. So in the exterior, the coordinate transformation gives you a unique map, a one-to-one map between R and U and V. So technically, even though you can solve that analytically for R larger than 2m, then you can solve uniquely for R in terms of U and V, put it in here, and you have a unique solution. I don't care about the interior, because the coordinate transformation is not valid in the interior. The rest of the space-time was not there before. The original line element was singular. So that's an extension to the coordinate. So there is no coordinate transformation in the interior. I want to be clear about that. Okay. And then you can also write this in terms of capital T and capital R. So you can use just the sum and the difference of V and U. And we write the line element in this way. Okay, so what you have is, oops. So if you forget about the angular part, the rest of the space-time, the two-dimensional space-time you parameterize by the null coordinates U and V, if you just write them in terms of T and R, it becomes basically a two-dimensional Minkowski space times a factor. Okay, so that's a very simple representation here. And this allows us to draw the Kruskal diagram that gives you the full overview of what's the space-time you have now. So So these are U and V, and I've drawn them in 45-degree angle, just so that this is my T and my R. So I can understand this diagram as some notion of time running upwards, right? Spatial direction here. Obviously, I'm suppressing the angular coordinates here, which is reasonable to do given that I have spherical symmetry. So the rest of the space-time is just simple. Okay, and because of this, which is also seen here because of the simple du dv, the beauty of this space-time is that, of course, light cones lie around 45 and minus 45-degree angles. This conformal factor doesn't really matter at all because light, null rays are ds equals 0. So I basically get the causal structure of a flat space in this diagram, right? And this is why it's so interesting. So R equals 0 surface, if I go here, give me u v equals 1, right? Which are these two curves here. So these are singularities, of course, which means I can't extend the space-time past this, but all of the rest is accessible to me as part of the extension. And of course, I recognize here the various regions that I know from the Eddington-Finkelstein extension. So this region 1 here is the exterior, right? This region 2 is the black hole interior, which I would get already with the ingoing Eddington-Finkelstein coordinates, right? This region 3 is the white hole interior. And this region 4 is just a copy of this one. So it's a region that is isometric to 1, which I just get because now there is nothing. So this would be what I got only from ingoing Eddington-Finkelstein. This would be what I got from outgoing Eddington-Finkelstein. But since there is no singularity or anything weird happening here, I should be able to extend the space-time. And if you look at the symmetries of the resulting space-time, then there is symmetry along that axis, which means this is a copy of that, right? And the time reversal also now follows very easily, again, symmetry along that axis, okay? So that's the full space-time. That's a maximally extended Schwarzschild space-time. Sorry? Because there is nowhere else I could go. I mean, intuitively speaking, here it's singular. And all the rest I have, there is no singularity, there is nothing. So it wouldn't be maximal if at some point my coordinates would become singular and I couldn't extend any further as in the original, say, Schwarzschild space-time. Or in the Eddington-Finkelstein ones. If you go to the Eddington-Finkelstein, so if you go to the ingoing Eddington-Finkelstein and you look at what is happening back here, of course, you will find that you can't, that if you try to get things to come out, you get a divergence, and then that tells you there is more space-time elsewhere, that way. Whereas here, you've hit all the singularities that you know are not coordinate singularities anymore, so you can't extend past that. And in any other direction, you've already extended that. You don't have anything singular happening to your coordinates. So that's all that it would be. Okay. Okay, now I want to discuss a little bit about these singularities. So yeah, I mean, we know, of course, that an invariant quantity diverges there. So we know we can't undo that for through a coordinate transformation. But I want to talk about geodesic completeness. Which of course gives you the proper definition of a singularity, okay? So a geodesic XA of lambda, where lambda is the parameter along the geodesic, for which the affine parameter lambda range is all R. It's called complete. Okay, so there's no beginning and no end. You go all the way, right? And you span all the real numbers with affine parameters. Okay. A geodesic that is not complete is called incomplete. Can somebody tell me why I need to say affine parameter here and I just don't say parameter? Sorry? No, it can be any geodesic. But why is affine important in this sentence? Okay, yeah. You're half right. I mean, the reparameterization part is important, right? So how are affine parameter, what makes an affine parameter affine? I mean, I can reparameterize a curve and find another parameter that is still an affine parameter, right? It's just that affine parameters are related linearly to each other, which means if I start from an affine parameter that covers all R, basically, then the other one will cover all R because it's just a linear transformation. A general reparameterization doesn't have that property. I can take, the tangent of the affine parameter or some other function, and I can map an infinite interval to a finite one, which means if I don't use the term affine here, I would render a geodesic incomplete just by a parameterization, which obviously wouldn't have any physical meaning. Then I have to find the right parameterization, right? So by using affine parameters in the definition, I make the definition robust in this respect. Okay, so a space-time is then geodesically complete if every geodesic can be extended into a complete one. Sorry? Because unit parameterization always exists. I guess I'll have to think about that. I guess you could. I mean, you need them. Yeah, I mean, yeah, you need to make sure that your definition of regularity is entirely robust. But I mean, as any definition, it's not unique in any way. It just have to be practical. Definitions have to be practical, right? They need to cover all of the cases you want. So I will call it just a space-time geodesically complete if every geodesic in this space-time can be extended to a complete one. Why do I say here extended to a complete one? Well, I can draw a geodesic that stops somewhere just because I decided to stop it there. So if I don't extend it, then I would kind of artificially have made the space-time geodesically incomplete. So I want to make the statement about, can I continue? Can the geodesic actually continue all the way? And if it can be extended, then I'll call it complete. So I'm saying, note all the geodesics I could draw in the space-time never end, basically. I go from one end to the other. And of course, an example is Minkowski. Okay. And I can apply that. I'm not going to write it down, but I could actually define as what would be a time-like geodesically complete space-time, one that all time-like geodesics can be extended to complete ones. Similarly, a space-like and a null geodesically complete. So I can just refer to any particular kind of geodesics, right? And that will be helpful occasionally. An important point is that one might be able to extend the space-time itself so I can start with something that is not geodesically complete. And I can extend it into a geodesically complete space-time. And there's a very simple example you could think about, which is take Minkowski space, take away one point, and then you'll have a space-time that is geodesically complete because there is a missing point. So every geodesic that would originally reach that point now is split into two parts with a missing point, right? So this space-time is geodesically complete, but then the moment you add that point back, everything becomes normal again, right? And that's an important exception because it helps me clarify the definition of what we will call a singular space-time. So we will say that if a space-time, so that's a manifold together with a metric, is geodesically incomplete, and it is not possible to render it complete, so what I'm saying is, if I have a space-time that is geodesically incomplete, and there is no way that I could render it geodesically complete by adding points, by doing something else, right? Then we say that M GAB is singular. So that will be our definition of a singular spacetime, right? And the whole notion is based on the logic that geodesics are these special preferred kind of trajectories in my spacetime, and I can use them to understand the properties of the spacetime. If I don't want to call a spacetime singular just because, you know, I've removed a point or I've done something funny, right? So I'm defining a spacetime to be singular when I can do anything to extend it into a singular spacetime. Okay? Okay, now I'll state a theorem. Suppose the metric is C infinity, it's infinitely differentiable. If any scalar built polynomially from the Riemann tensor and its covariant derivatives, for example, Ricci scalar, Ricci tensor contract with itself, Wetzmann, diverges along an incomplete geodesic the spacetime said to have a curvature singularity. An example here is, of course, Schwarzschild itself. Okay, so this theorem links singularities with divergence of curvature invariance, and it tells you that you can actually calculate curvature invariance, and if you see them diverging, then you can infer that the spacetime is singular, but the converse is not true, right? So the fact that we've seen that at r equals 0 in Schwarzschild, you have a curvature singularity is enough for us now to infer that this is a singular spacetime by our broader definition, right? But I can have a spacetime that has no curvature singularity. In fact, I can have a spacetime where the curvature is 0 and it's still singular. Okay, and the most characteristic example, of course, what people use in this case is you start with flat space, a flat sheet of paper, you fold it into a cone, like that, right? You create a tip. The tip is singular. because geodesics end there, but the space-time has everywhere zero Riemann. There's no curvature invariance that diverges. Everything's fine. Okay. So singularities are not necessarily related to curvature, though if you have a curvature singularity, then it is a singular space-time. Let's see the term. Do I? No, I mean, if you go by continuity, nothing happens, right? You don't really need to think of what is happening at the tip. By continuity, the space-time has zero curvature everywhere. So all the geodesics will be incomplete, though. So, Sudipta, do I need to? Should I take a break? Should I take a break?
No, it's okay. It's up to you.
Huh?
It's entirely up to you.
Okay, I'll take a 3-minute break for people to just clear their minds, and then I'll move on to the next. I don't have it handy, but I can find it for you if you want. Okay, so I now want to talk about Penrose diagrams. I'm going to first talk about the Penrose diagram in Minkowski space, and then I'm going to go fairly quickly to the Penrose diagram of Schwarzschild. Probably some of you have already seen Penrose diagrams, but in the tutorial in the afternoon, the Penrose diagram of Schwarzschild will be done in more detail. Okay. So why am I interested in Penrose diagrams? Well, the Kruskal diagram is already quite instructive. As I discussed earlier, if you go in here and consider an event and try to draw its light cone, you can actually draw it without even thinking. You know that because of this property here, null rays just move in 45 degrees. So it's easy to understand what is causally connected to what is in the future, what is in the past, what is neither in the future nor in the past, and so on and so forth. So the Kruskal diagram already has this good properties, but what's hard to discuss in terms of the Kruskal diagram is infinities, right? So the reason, so what we're trying to do here is we're trying to find even better coordinates than the Kruskal ones, which will preserve the nice property, the fact that the light cones are trivial in this coordinate system, but give you a nicer exposition of infinity. Okay, so we're going to start with Minkowski and try to do that for Minkowski, and then we're going to see that since actually what we're interested is really to change the structure of infinity, and since Kruskal is asymptotically flat, then whatever we do in Minkowski will very easily pass over to Schwarzschild. Okay. So we're starting with this line element. And then we introduce coordinates which are very, very similar to the Eddington-Finkelstein coordinates, because of course they are the null coordinates, v and u equal constant, correspond to ingoing and outgoing, I mean, to left moving and right moving light rays. So these are null coordinates. And I can, of course, write T and U, T and R in terms of U and V as well. And then the light element takes this simple form. And notice the similarity, if I forget about the angular part, notice the similarity between this and that, right? So the capital U and V here play the role of the small u and v there. If I were to write that in terms of T and R, of course, I get the usual Minkowski structure of the capital T and R there, right? Okay, now what I want to do is bring infinities to a finite point, right? And I'm going to do that by making yet another coordinate transformation. I'm using twiddles here to differentiate the capital U and V from the ones I've used before. So this maps the infinite, all of R basically, minus infinity to infinity, to the open interval minus pi halves. Okay, so I've compactified, right, these directions and mapped the infinite, all of R in a finite interval. And of course, I have to be careful because R is larger or equal to 0 in Minkowski, right? I can't take negative values, which imposes a restriction. V twiddle should be larger or equal to U twiddle, okay? Then, of course, I can go and calculate the U is 1 over cos. And if I replace all that back in, Wait, this is too high, eh? The line element takes this form. Okay. So I've written now Minkowski in terms of these compactified coordinates. I've brought infinities to a finite value of the coordinates. But I have a problem. And the problem is this factor here, right? So as you can see, when I'm trying to reach infinity, which would mean that u and v goes to pi halves minus pi halves, that thing becomes 0 and it's to the -2. So I have a singularity. Yeah. Sorry? V minus u. Okay. Sorry. Yeah. I have it as u minus v here, but I'll trust you. It's taking my coordinates. Yeah, so I get a divergence at infinity, right? So obviously that's not great, but the clever part is exactly that I don't care about this factor here. If I'm only interested in the causal structure of space-time, then null rays, null trajectories, null surfaces are oblivious to this. So I can create a new space-time, I will call S, with line element ds twiddle. So let me write it down. Consider ds twiddle square, which is some suitable factor times ds. And obviously these two spacetimes will have the same conformal structure. If ds is 0, then ds twiddle will be 0, right? And vice versa. So what I'm going to choose here is that if I choose L, if I choose lambda to be this, then my ds twiddle is just that bit. Okay. So this will have the same causal structure as the original spacetime, right? And I've managed to bring infinity at finite coordinate. But I'm not done yet. So the infinity is not part of the original manifold, right? So that's why these are open intervals here. So what I'm going to do now is I want to add the points at infinity to the manifold to create a new manifold. So I started with a manifold M and a metric GAB. I'm going to end up with a new manifold, say M twiddle, and a new metric, C twiddle, completely different space-time, right? But with the same causal structure. That's the idea. So now add the points at infinity to our manifold. And then we can create this new space-time, new manifold, new metric, which you can draw here, right? And which are the points at infinity? Well, I'm going to go and list them here. So I'll have u minus pi halves, v pi halves, which corresponds to if you follow the coordinate transformations there, if I push r to infinity and I keep t finite, then u will go to minus infinity, v will go to plus infinity, and that corresponds to that point, right? So this is spatial infinity. I'll denote it as I naught, right? And that is going to be, say, here. I naught, okay, where u is minus pi halves, and v twiddle is pi halves, okay? I'm going to keep the Kruskal diagram, so I'm going to continue here. So then I have u twiddle pi halves, v twiddle pi halves, which corresponds to u plus infinity, v plus infinity, or e going to plus infinity, and r being finite. Right? And again, you can follow backwards the transformations to verify that. And this is a future. This is going infinitely into the future. So I call it future temporal infinity, denoted as I plus, right? This is sitting here. Okay. I then have u minus pi halves, v minus pi halves, right? This is u plus infinity, oops, sorry, minus infinity, v minus infinity, or t minus infinity are finite. And this is, of course, the past temporal infinity. I will denote this as I minus. And it's sitting here. Then I have to take u twiddle to be minus pi halves, while v twiddle is neither plus or minus pi halves, right? And this corresponds to u going to minus infinity, v kept finite, or r going to infinity, t going to minus infinity, with R plus T finite. So, and this is past null infinity. And I will denote it as scribe minus. So here I'm keeping one of the null coordinates finite. I'm sending the other one to minus infinity, right? So this is past null infinity. And similarly, I take V twiddle pi halves. U twiddle is not plus or minus pi halves. And that corresponds to U now being finite, V going to plus infinity, or R going to infinity, T going to infinity with R minus T finite. And this is the future null infinity. Denoted as scribe plus. So these two are here and there. Okay. And remember, where is it? Well, I also have this condition, which tells me that only that half of the diagram is relevant, right? It's Minkowski. So if I go and add all of these points, I naught, I plus, I minus, and the points along scribe plus and scribe minus, then I have my full new manifold with its boundaries. Now the manifold has boundaries, before it didn't. If you notice now, I'll write it here. All of the boundaries are the locus of points where lambda is going to 0, where the conformal factor that was relating the original metric with a new metric vanishes. Okay? So this is basically, and you see, of course, the similarity with the Kruskal diagram. Basically, the coordinate transformation I've introduced does really nothing here away from infinities, right? And it just brings infinities to a point. It allows me to recognize different points at infinity, right? So let's try to spend a second trying to understand these points at infinity. Now I can just erase the Kruskal as well. So I can now be more abstract. This is Minkowski space now, this nice triangle, right? And I can think of an event in Minkowski space, call it P, and I can ask myself, what do different type of geodesics do? And if I try to draw, say, with blue, the null geodesics, then of course I can have a right-moving null geodesic that goes here. So it goes to scribe plus, right? I can have a left-moving one that goes here, bounces off, and goes again to scribe plus. Why does it bounce off? Yeah, it doesn't really bounce off. It just passes through r equals 0 and continues to infinity in the other direction, right? But the way I've compactified it now, that looks like it's bouncing off, okay? Or I could have I could extend these. Remember, I can maximally extend the geodesics here. This is geodesically complete. So I can go in the past, and they will end up in scribe minus. So now geodesics really start from scribe minus and end up at scribe plus, right? So you can think of scribe minus and scribe plus as the origin and destination of null geodesics. Then you could take a time-like geodesic, and a time-like geodesic would start in here and will end up in I plus. And if you extend it to the past, it will start from I minus. So all time-like geodesics start from I minus and end up in I plus. Okay? And finally, if you start from P and you ask yourself, okay, where does a space-like geodesic that contains P ends? It will end in I naught. Okay? So the beauty of introducing the Penrose diagram, even already in flat space-time, which we knew the causal structure is entirely trivial, is that it splits the infinities in time-like space-like and null infinities, and then it tells us how to draw geodesics and how geodesics behave near infinity. And it tells us that actually different geodesics reach different infinities. Okay, and that's the important message. Okay, so how does that work in Schwarzschild? So let's go back to the beginning. Remember the similarity that I pointed out to between the small u and v that I introduced in Minkowski space and the capital U and V that I introduced in Schwarzschild, right? So this is exactly what you want to do here. You want to start with a maximal extension of Schwarzschild, which is, of course, what is depicted in the Kruskal diagram, right? And now you will introduce U twiddle and V twiddle, not to be confused with the ones I used for Minkowski, obviously. It's using the same symbol in this way. Again, to avoid confusion, the U and the V are the ones for the Kruskal one in your notes. So I'm going to now try to compactify the Kruskal U and V by using, again, the tangent, U twiddle, V twiddle, right? So now I will get so I'm mapping the infinite intervals minus infinity to infinity for U and V to the open minus pi halves in the twiddles. In Minkowski, I had this restriction, right? There is no such restriction in Kruskal. U and V run along everything, along all R, right? So I'm not going to get half a diamond, right? I'm going to have more coming this direction. Okay, there is no restriction between U and V here. And as before, you will get a du dv cos U twiddle cos V twiddle to the -2 du twiddle dv twiddle. And you will, of course, have the same problem. So if you look at the metric that we use, the line element that we use to construct the Kruskal diagram, it was, of course, regular everywhere except of R equals 0. That was the whole point, right? But now, if you swap du dv that is sitting in that line element with du dv twiddle, you're going to pick up this factor, which again diverges at infinity. So same as Minkowski, you compactify the space at the expense of things diverging at infinity, and you're going to deal with it in exactly the same way. we're going to select lambda, which is cos u twiddle, cos v twiddle, okay, which which goes to 0 as these guys go to pi halves or minus pi halves, right? And hence you will define ds twiddle as lambda ds squared with this is the Kruskal, right? Okay. So this is the same, exact same process as before. And you're going to end up with what is now a new metric, which has the same causal structure as Schwarzschild. And again, if you think of these transformations at small u twiddle and v twiddle, u twiddle and v twiddle behave the same way. So you're not really affecting the central part of the Kruskal diagram, right? But you're just changing the behavior near infinity, right? By compactifying infinity. So now, of course, you need to identify the points at infinity and add them to the manifold. Okay, and then you create a new manifold, again, with a new metric. Now you're going to have a boundary, as before, and you're going to have a space-time, a new space-time, which has the same causal structure as the maximal extension of Schwarzschild, without, of course, being the same space-time. Okay, so, of course, asymptotically, Schwarzschild is Minkowski, right? So the points at infinity will be the same as in Minkowski. So I'm not going to do that in any detail, but again, it will be done in the tutorial in detail. So you know then that if I were to draw u twiddle and v twiddle, right? You know that I would get the same points at infinity as Minkowski. I have, remember Kruskal, in Minkowski, my space-time ended here. Kruskal has symmetry left to right. So I have to have another, and I had a second asymptotic region in Kruskal. So I will have the second set of points on the other side, right? So I will get them here too. This is the second asymptotic region. Right, then I need to think of r equals 0, which corresponded to uv equals 1, which after the coordinate transformation means u twiddle plus v twiddle equals plus minus pi halves, which are now the straight lines sitting here and there and connecting these points. Okay, so the hyperbolae ended up being straight lines in this diagram, and that's my full compact space-time now with the new metric. So this is basically the Penrose diagram of Schwarzschild. And of course, these are the horizons, right? Because r equals to m. was before u equals 0 or v equals 0. So they remain at u twiddle equals 0 or v twiddle equals 0 by my transformation. Okay, so they're still the diagonals, the diagram. And we tend to draw this diagram again. We don't need the axis. We just draw the singularities as curly. These are the I naughts, I plus, I minus, R equals 0 in the future, R equals 0 in the past. So exterior, black hole interior, white hole interior, second version of the exterior. Okay? And similarly to before, if I select here, I pick this asymptotic region, and I select the point P, and I start drawing null geodesics. Now, right movers go to plus infinity, to scribe plus, sorry. Right? Left movers can end up in the singularity, can cross the horizon and end up in the singularity. And if I extend this to the past, this can be coming from the singularity, whereas this will be coming from scry minus. Okay? Now, similarly, the same colors. Space-like surface from P will end up in I naught. And if I start a time-like geodesic from P, it could end up in I plus, and in the past it could end up in I minus, right? But it could also end up in the singularity, right? Okay? Or come out of the white hole. Okay? So now we have a diagram that makes it easy to discuss infinities and see what is the fate of observers, and we'll come back to that later. What is the fate of null geodesics and so on and so forth very easily without actually understanding the subtleties of the space-time. And at the same time, you know, has the beauty of the Kruskal diagram that light cones are very simple. None of the, again, this is not the cheat here. The price we had to pay is that this is not the diagram of the original space-time. This is a diagram of a new space-time, a new manifold with new metric, right? But so it's only to be used to understand the causal structure. It's only to look at the causal structure. Any local property doesn't reflect the original manifold. So the curvature at the point of this new space-time, the new metric is not going to be the same as before. Okay, how much time do I have left? Okay, perfect. Okay. So let's now, by sheer intuition, try to think of how would the space-time diagram of a star collapsing to form a black hole would look like. Okay, so so I mean, I should say before embarking on this that obviously you could think about doing this now, following the recipe for any space-time, right? You can just say, let me start with my metric. Let me introduce double null coordinates, which are intuitively defined. They're basically, you're introducing coordinates in which the ingoing and outgoing or left or right moving null geodesics will follow coordinate equals constant trajectories, basically, right? So let's introduce them. Let's swap, basically, two of my existing coordinates direction for these two. Let's suppress the other two coordinates and go and look at this two-dimensional space, right? I can compactify the space, as I did, try to bring infinities to a finite point. This will generically make my metric singular. It will introduce a conformal factor that generically will be singular at infinity. So let's swap the metric for a conformal metric just by multiplying by this conformal factor squared, right? So then I create a new metric. Infinity now lies that conformal factor equals 0, right? I create a new metric. Then I go and add the points at infinity to the manifold. I create a new manifold, and hence I have the Penrose diagram of the space-time I started with, right? So this is a recipe that you could apply, basically. There are subtleties to this recipe. How do you choose which coordinates to suppress and to draw the diagram and all this kind of stuff? But let's leave that to one side. We'll come again to that when we talk about care, right? But it could be done. So by the same token, then let's try to think about what the Penrose diagram of a collapsing star into a black hole would look like. So who wants to guide me through how to draw this? Anybody? How would the diagram, the Penrose diagram of a static star look like? Exactly. So the diagram of a static star would just look like flat space, because asymptotically it would be Minkowski. There are no horizons or anything like that, right? I'm only allowed to have half the diagram because R is positive, right? And somewhere here would be the surface of the star, and that here, the green dust part, would be, so that's the surface at R equals constant, right? And obviously it starts from I scri minus and goes from scri plus, because if I'm a point at the surface, if I'm an observer sitting at the surface and I'm treading a time-like trajectory, okay? And so that's the star, right? Now, we know the black hole part, right? It has to end up looking a little bit like this. How much of that diagram should I use? Obviously, the left side is completely irrelevant because it's just a copy. The white hole is also irrelevant. It doesn't really exist because it doesn't form from collapse. It just comes from the time reversal. So it's going to be that top part that is going to be there. So I want to end up looking like this, but I want to start looking like that. Okay, so if I go here and draw on the top, kind of the part of the Schwarzschild diagram, right? So this is the horizon, scri, the singularity, I naught, right? What would the surface of the star do? Well, if the star is collapsing, the surface will start from being outside the horizon, of course, but eventually it will have to probe in and go inside the horizon. So I'll draw it as such, a time-like curve that crosses the horizon and reaches the singularity at some point, right? If I try to extend this in the past, I will have to reach the I will have to reach I naught, because time-like geodesics start from I naught, and I have to reach that picture. Originally, R equals 0 is here, and this is the interior, the stellar interior. Okay, R equals 0 is here, but R equals 0 is also here, so somehow they will have to meet somewhere, right? And then the horizon won't exist in the beginning, so it will actually have to pop out somewhere there, right? And this is the only way the diagram could look like. So you have to believe me that that's the correct diagram. And this is kind of the beauty of Penrose diagrams. It's one of the reasons I drew this. I mean, first it demonstrates kind of de facto that all of this part here is irrelevant, right? But also it's the beauty of a Penrose diagram that, I mean, it is so abstract that I don't even need to know the space-time exactly to draw the diagram, okay? And I can understand things intuitively just by drawing the diagram. So I'm gonna stop here today, and tomorrow we're gonna go into discussing past, future definitions of horizons and black holes and so on and so forth, and then go to the Kerr space-time. Okay. Thanks.